Hey, good afternoon. This is lecture 6, and assignment 2 has been uploaded, and the deadline is next Monday, 11, still 11 a.m., okay, in the morning. I will set the deadline for this assignment 3 as discussed. I will set it at 11:59 p.m. as requested. Okay, and I also want to say we do not accept late submission. And particularly now everything is electronic, it's very easy for us to track. Okay, so if you submit your assignment late, I'm sorry, we cannot accept them. For assignment 1, we try to be a little bit more accommodating. We will try to accept some assignments as long as it's reasonably, if you are 5 minutes late, we are normally okay. Right, so the TA will decide together with me. Okay, so if you have, it's your own responsibility to learn how to do this properly. For example, I got some TA reported to me that some students claimed that they submitted an empty one, a blank one, before the deadline, and didn't use a submit button or accidentally used only the save draft. Okay, this kind of technical problem, you need to learn how to eliminate as soon as possible. Okay, so starting from assignment 2, we do not like to deal with a situation like this. Another thing is the exercise classes. We have 3 exercise classes slots every week, and this is a lot of resources we invested into this, and you are strongly encouraged to participate actively. Okay, we have 3 slots tomorrow. Okay, so what did we learn last lecture? This is some quick recap. What we learned, very important stuff, 2 impossible engines. So these are the statement of the second law. Some students ask, how do you know that this is true? Okay, so the answer to this question is similar to the answer to how did you come up with the first law and how did you come up with the 0th law. These statements are basically largely due to observation, experimental observation. And you can think of it this way. People have tried to come up with something like this. That is to say, to convert all the heat into work. Right? So that would be nice. If you can extract heat from the environment, you get a lot of work done. Okay, so that is not possible. So this is, that's why, again, let me emphasize, this is why this notation is there. There's basically an engine which is not possible. Okay, equivalently, I already told you this is the equivalent statement. You cannot get heat flow like this. You cannot just exclusively get heat from the cold reservoir and transfer to the hot reservoir. All of them transfer to the hot reservoir. That is not allowed. Okay, and some students also ask, what about the fridge in the kitchen? The fridge in the kitchen, you might think it's something like this, but actually it's not quite the case. Okay, because there you have to plug in your fridge to the electrical socket. So that is actually a special type of engine, which is actually is just a normal engine running backward. We will discuss this later, don't worry. Okay, so you need to prove the equivalence of the 2, and you have to then come up with this kind of scheme, the logical scheme. I have shown you one and you do the other one. And in this chapter, you have seen the name Kano mentioned so many times. This is a very, very important name for thermodynamics, and you are required, if you want to master this material, you are required to really digest all of them. The first one, the easiest one, which you have seen probably from first year physics, is the Carnot cycle. So the Carnot cycle, you can use it to build Carnot engine. Carnot engine. This is something you have seen before. So for us, for the purpose of this course, we need to be a little bit more specific. So when we mention this Carnot engine, I gave you the definition. So the important ingredient are the following. This engine must be reversible. Carnot engine is reversible, and you only have two reservoirs, only two reservoirs with at theta 1 and theta 2. So sorry, this is at. And this theta 1, theta 2, today we are going to, very soon, actually very soon, we are going to attach meaning to them. And then there are only two reservoirs, and they are characterized by theta 1 and theta 2. And this has to be a constant. This and this comma. These are constant. Okay, and this is how we want our Carnot engine to be. Okay, then it comes to Carnot theorem. Carnot theorem is about efficiency. So this is Carnot theorem in word. If I have another engine, let's say hypothetical engine H, and this engine cannot be more efficient than the Carnot engine operating between the same two reservoirs. Right? This is a very, very cute result, but you can prove it. Okay, there's a message. So in page 10 of the last lecture, recognize, so here, this one, using this. Where's page 10? Page 10 of the lecture note, or? Okay, I will let you phrase the question later, okay? I don't, okay, PowerPoint, the draft, right? The draft PowerPoint. Page 10. In some textbook. Okay, so in some textbook, it depends on which one. It's better if you show me. So here, last time I proved one direction. Okay, so now the quick answer to your question is this. If I ask you to prove not K implies not C, you have to come up with a slightly different drawing. Otherwise, it won't be so simple if you just reverse the logic. You see, the way I have it here. So last time when I did this, it took me quite a bit of talking to get to this point, right? So from here, from the left to the right, right? So now this allows you to, with all this talking justification, I managed to draw it like this, right? I managed to argue why this Q2 has to be the same as this Q2, and then I will come up with something like this, okay, which is a not K. So if I ask you to start from not K, it's not that easy to add things back in. Okay, I kind of, I suspect this is what you are asking. So can I just say my word differently and then argue that this step I can reverse it by adding Q2 back in and then break this composite machine into 2 and then I come back to here. That is not what I want to see actually. Okay, so what I want to see is really you start with not K and you think a little bit harder to see how you can arrive at some violation of the closest machine. Okay, that is a not C. Okay, so this is the exercise which you can try. It's not that difficult. It's also quite fun. So the good thing about this part is you can use all these engines. So that's why I start from here. I start from these two. So these are the two scenarios that I gave you, which as for you to use as a starting point. And eventually these are equivalent to the second law. It's just it's stated in this funny way. Okay, and if you remember, for this Carnot theorem, it's about efficiency. So this is about efficiency. We can also prove it. This is about efficiency. Okay, so I already saw it. I just want to very quickly recap for you. So if you have a hypothetical engine H, the efficiency of this engine, if you say nothing about this engine, the only thing you know is this engine is operating between the same reservoirs, which means the temperature will be the same. The only thing you can say is that the efficiency cannot exceed the efficiency of the Carnot engine operating between the same two reservoirs. Okay, so this is in general. So this is the general case. General. Okay, this is a full stop. You cannot say much more than that. So why do I need to say this? Because very strangely, every year students make this mistake. Although it's kind of straightforward at the beginning, but wow, this mistake comes up all the time. So if this engine, if this is reversible, if this hypothetical engine H is also reversible, then you have to satisfy two requirements. So you have to satisfy this requirement plus this requirement. Okay, so from here, you put these two together, you get the equality. Okay, it's worth spending 2 minutes on this, so you make sure you don't forget this, because when we deal with closest theorem, the same argument come up again. Okay, so this is really written down here. Okay, and the mistake, usually the mistake, sometimes you see and it breaks your heart, is students say when the engine is reversible, the second one is true. They forget that this is more general. This has to be applied. The first line has to be applied. So they only write the second line. And then they get confused because they don't know how to reach the equality. Okay, and then the other thing we will need today very quickly is we apply, sorry, how should we say? We test our engine, our engine with an ideal gas. Okay, so here you can get very straightforward prediction. So you basically get the ratio of the heat flow. Okay, so you get Q2 divided by Q1 is theta 2 divided by theta 1. Okay, so this is, as I say, this really means the absolute value of this heat transfer is related to the ratio of the temperatures. And this is very important. I already boxed it last time. I'm going to box it once again. This is Richard Feynman. We will see something similar today, expressed in terms of T, the temperature you are familiar with. Okay, right now I use a different symbol. Basically, this theta, when we have the ideal gas, we try it, right? We try to analyze a situation using the ideal gas. And therefore there, this theta really is the temperature of the ideal gas for 1 mole of ideal gas. Okay, so this goes into the equation of state, if you remember. Okay, so Richard Feynman called this the heart of thermodynamics, this equation. Okay, you will appreciate this very quickly. I also gave you another way to do that for ideal gas. That is, we start from the first law, and then we divide by theta, and then we change a variable because we took advantage of our previous knowledge that the internal energy is only a function of temperature, and I arrived at this result too. Okay, so this is the heart of the subject. Thermodynamics. Okay, so we are going to try to appreciate this more. Okay, so as promised, long time ago, 2 weeks ago, we say after we learn how to construct the Carnot engine, we can define the temperature in a different way. And this definition uses a Carnot engine, and it does not appeal to any particular system. You do not need to use an ideal gas. Remember, we talk about using ideal gas to do it. So that allows us to establish the notion of the temperature. And then the first law, the 0th law, tells you there's something called the temperature, and that temperature is a property at thermal equilibrium. Okay, and if you want to establish this scale, we mentioned that we can use an ideal gas to do that. Okay, and that is essentially this result here. If you think about that, you use it all the time, but historically, this defines some kind of scale, right? So if you take an ideal gas, if you look at the product between the pressure and the volume, you can establish a scale, and the scale is defined such that this R gives you 100 units between the ice point and the boiling point of water. So this is some kind of scale. Okay, and now we are going to do something which does not depend on the substance, the working substance. It doesn't need to be an ideal gas. Okay, so how do we do it? How do we construct something like this? How do we construct the argument? It's the same thing we talk about. Basically, from the recap I gave you earlier, we can say something like this. We can say something very strong. We can say this: all reversible engines operating between this operating between the same reservoirs. So I will say a given pair of reservoirs. Okay, what happens to all these engines? These engines are equally efficient. Okay, it doesn't matter how you build this engine actually, as long as it's reversible. It doesn't need to be based on the piston cylinder and ideal gas. It doesn't need to be like that. You can come up with very clever engines, but the point is you cannot exceed the efficiency of the simplest engine, which is the Carnot engine. Okay, and therefore, as a consequence of that, you have this statement here. Okay, so we talk about efficiency. And efficiency, in this case, they are equally efficient. It means it doesn't really depend on the internal structure of the engine. And what can it be? It can only depend on the reservoirs. So this is the meaning. It can only depend on the reservoir. Okay, and as a reminder, the efficiency has this factor here. And this factor of, let's say, between A and B. Okay, doesn't matter which one is high, which one is low, but there's a ratio. This ratio of heat flow enters the efficiency, right? Remember how we define it? We define it as the heat you need to inject. Efficiency is defined as the work divided by the heat you need to inject. Defined as what you get over what you pay. Okay, so here you have this factor. And from this theorem, from this statement up there, we know the efficiency only depends on the reservoir and nothing else. And the reservoir is characterized by the temperatures, right? So the reservoir is characterized by the temperature. So the efficiency can only be a function of temperatures and nothing else. Okay, so because of this, the efficiency can only depend on the temperatures of the reservoir. How do you label the reservoir? In my slide so far, I used the symbol theta 1, theta 2. Okay, so the reservoir are characterized by theta 1 and theta 2. Okay, so I can write something like this. The efficiency, therefore, has to be depends on this ratio. Right? This tells you the efficiency. And this can only be some function of temperature. Okay, let me use AB in this case, A and B. Okay, and nothing else. And now, what do I do with this this kind of statement? I'm going to build my engine again. I'm going to build this engine. Let me take some space here. Push this a bit this way. I'm going to have a Carnot engine, right? Because I want it to be reversible, so I can write down this statement. So I will have a Carnot engine C, like that. This is the engine you know very well. So I will have Q1, and then I will get some work. And here I will have Q2, and I dump all this heat to theta 2. Okay, now I want to do more. I want to connect this to another Carnot engine, C2, and then I want to dump the heat to theta 3. Okay, so I have Q2 here and Q3 here, and I get some work out. Okay, let's put all this symbol in. So what we have here is the following. We can then write Q1 divided by Q2. Has to be only a function of temperature. Okay, so if I plug in another engine, I will have the other equation, and Q2 divided by Q3. Again, it doesn't depend on the structure. It has to be the same function of temperature. Okay, so this is a Carnot engine, this is a Carnot engine, and I already arranged it such that all the heat flowing into theta 2 will flow out again. Okay, so this reservoir becomes an intermediate reservoir, so I can view the whole thing here as a composite engine again. So I can regard this as a big Carnot engine. Okay, so this is equivalent to a Carnot engine, another Carnot engine. Why? Because this is a Carnot engine, is reversible. This is a Carnot engine, is reversible. So I can flip all the arrow and I will get another Carnot engine. So I will use C as the composite engine, which is also a Carnot engine. Okay, so for the blue one, what we have then is the same thing. This Carnot engine only see the top reservoir and the bottom reservoir. So I can have Q1 divided by Q3. Again, it's only a function of theta 1, theta 3. Okay, if you multiply these two together, the green one together, you get Q1 divided by Q3. And you get this result. But when you look at the left-hand side, right-hand side, you have this theta 1, theta 2, multiplied by theta 2, theta 3. And this has to be only a function of theta 1, theta 3. This probably sounds familiar to you because we did something similar. Very slightly more abstract. We don't really want to mention a function. We just look at the argument, look at the structure. Okay, so the right-hand side is only a function of theta 1 and theta 3. And the left-hand side is only a function of theta, it's a function of theta 1, theta 2, theta 3. So this theta 2 has to disappear. Okay, and how can it disappear when you write it like this? This is a product. Okay, so for this to disappear, then you have to, for this to be true, this has to, you need to somehow cancel this. Okay, so you need to cancel this. To cancel this, the only possibility is this function has to be some kind of ratio. So to cancel theta 2 in this manner, then my function f has to be written as a ratio. It has to be written as some kind of ratio, say something like this. Okay, so I choose to call this function g some temperature. So this is the symbol we have. You get this point? Right? So here, when I look at this, Q1 divided by Q3, I don't really know what is happening here because I did not specify this function f. It can be all kind of funny structure. But after analyzing this, mathematically, I know this function f has to be some kind of ratio that you can separate like this. So the top is only a function of theta 1 and the bottom is a function of theta 2. Then I might as well assign this G to be the temperature. Really this is what we call the thermodynamic temperature. Really the temperature we are more familiar with. Okay, so from here, we can write something, we can complete this. So the efficiency in this case, if I write out everything, okay, suppose I have, if I only look at any pair, say between theta 1 and theta 2, this will give me 1 minus T2 divided by T1. Okay, and this is called the thermodynamic temperature. Okay, Or another way to write this is I have my Q2 divided by Q1 is T2 divided by T1. And again, the sign convention is built in here. So this is really the absolute value of Q, the heat flow. Okay, so these, if you compare, so from this Carnot engine, I can establish a temperature called the thermodynamic temperature. From the ideal gas experiment I did last time, here, I have this result for you, right? So if I use thermodynamic, if I use ideal gas, so this is the temperature scale you learned before, okay? You see, this is the same expression, okay? So it turns out that we might as well define the thermodynamic temperature as the temperature given by the Kelvin scale, which is based on the ideal gas. Okay, but here, this is really because of the calculation I did before. And up to this point, this T2 divided by T1, this is the thermodynamic temperature, which is defined up to some kind of proportionality constant, but there's no more offset. Okay, so this is one way to define this the notion of temperature without resulting to any specific detail of the engine. The only thing I say is I have a reversible engine operating between the same reservoirs. Okay. This is I don't know how easy it is for you to accept this. The first time I saw something like this many years ago, it feels really difficult to appreciate the power of this. And if you have time, there's some nice writing in the textbook by Steen. Okay, so I give you the page. If you have half an hour, it's good to digest this maybe with your favorite coffee. So this is about he gave something analog to this case, but he used the example in mechanics. So basically, he come up with this equation. The ratio between the mass is given by this. Now, if you look at the mathematical structure, of course, you know this has to be true, right? Because you know F equals ma. But now the thing is, you want to be able to define something which is independent of the way you apply force. Okay, so you want some intrinsic properties. So this intrinsic property is the masses, and you don't want to care about how you apply force. Okay, but suppose you know how to measure the acceleration, you know there's something like this which has to be satisfied. Okay, the thermodynamic equivalent is this. We want here our variable turns out to be T1 and T2, and suppose we know how to measure the heat flow, we will be able to define this ratio of heat flows to be related to the ratio of the temperature. And likewise, you know very well, if you can measure the acceleration very well. Now, be careful, this is the inverse, but doesn't matter. If you know how to measure the acceleration very well, even if you don't know how to apply the force, you can deduce the property of this body. And that property is the intrinsic property called the mass. Okay, so this is worth reading, okay? Page 98, actually starting from 98 to 99. It's good. In other textbook, you see this result, and very often you don't, if you're not careful, if you don't read all the lines carefully, after you finish this, you suddenly say, hey, why is it the case? But here, there's some preparation for you. Okay, so have a look. And now, I want to ask this question. we keep saying this engine, this Carnot engine is reversible. Okay, so you will ask what is the reverse of this. Okay, so from now on, I will use I will use theta 1, theta 2. Okay, so I reserved this symbol before, but now we can just label it as theta 1, theta 2, T1 and T2. Okay, we have seen this engine many times. This is the work you get, and this is, say, Q1, Q2. So if I want to reverse, what I will have is I will have to flip all the arrows. So if I flip all the arrows, I will get something like this. I will get so this is a Carnot cycle, right? If an engine is reversible, I can reverse everything, and it will look like this. Sorry, I say Carnot. I don't want to jump so fast. I will say this is an engine which is reversible. Why is a good symbol? This engine is reversible. Basically, this engine is reversible. Okay, if I reverse everything, I will have T1, T2, and I will have this. Okay, so this, look at this. Now I'm going to give a symbol R. This is a reversed of the engine. And look at this again. This is Q2, T1, Q2, Q1, and T2, T1. And do not confuse yourself with this engine. This is also Q2, this is Q2, and this is Q2 because there's nothing coming in, right? So this Q1 and Q2 are the same. This is not allowed, but if I draw one more arrow, this becomes acceptable. And that's indeed this one. Okay, so this is a reversible engine running backward. But what I really want is to drive a Carnot engine backward, because there I know how to express Q2 divided by Q1. Okay, so Carnot engine, for the Carnot engine, we already know how to express the ratio of the heat flow. So let's say for the Carnot, we know Q2 divided by Q1 is T2 divided by T1. We just established this. Okay, and this will help us a lot to get some concrete results. If you run this Carnot engine backward, what can you do? The first thing you can do is you can build a refrigerator. What is this object doing? This object is basically trying to extract heat from here and dump it to outside, right? So if you open your fridge, T2 is lower. Okay, so refrigerator is used to extract heat at T2. Okay, so we can define something that looks like efficiency, but I don't like to call it efficiency because some people will get confused. I will explain why. I like to call this the figure of merit. This is something like an industrial standard, right? Now, this is defined as what you get divided by what you pay. So this is kind of the opposite from the heat engine, because what you want to achieve is to get as much heat out from T2 as possible. You want to cool down your system, and what you have to pay this time is the work. This is your electricity bill. You plug this onto the wall. Okay, so if you know this is Carnot, you can write one more step. So this is Q2. This is Q2 here, and then you have Q1 minus Q2. Is it correct? Let me see. So Q2 plus W is Q1. So W is this. Okay? And if this is Carnot, you can instantly work out the ratio. And why do I say I don't want the word efficiency? The reason is this: if T1 and T2 are very close, this shoot up. So you can get a figure of merit which is very, very large. And some people will think that this violates the law of thermodynamics, right? Well, how can you get an efficiency which is more than 100%? That is because of our definition, as simple as that. It doesn't violate any thermodynamic law. So here, this figure of merit, still it tells you that the fridge is working well when the temperature difference is not too large. So this is large when T1 is close to T2. Okay, this is familiar. The other thing which is maybe less familiar and is also based on the identical drawing is what we call a heat pump. A heat pump is actually great. I haven't, now thermodynamically, this is really a beautiful stuff, but I really haven't seen too many people installing this. When I was studying at Cambridge, I learned from some friends that one college is installing a heat pump. Didn't get a chance to see it. A heat pump itself is expensive, just like if you want to buy equipment from Fortress, you have to pay for this. Okay, so this thing here becomes a heat pump, and then you have to pay. Okay, remember this, we have to pay. And then we will come back to this soon. Okay, what is the heat pump doing? The purpose of heat pump is again a bit different. What you want to do is to extract heat from the environment. And what you then want is to dump the heat to your room, for example, to warm up your room. Okay, so that is a bit different. So if I want a good heat pump, if I want to define a useful indicator, then my figure of merit has to be defined like this. So this is the figure of merit for the heat pump. I want to, now the higher the number, the better the pump. Okay, so what should I do? I want to be able to get as much heat as possible to my room. Okay, and at the same time, I want to pay as little as possible. Okay, so this is, you see, this is a bit different, and don't get confused. And it turns out that this is, okay, if this is Carnot, following the same thing, if this is Carnot, you know how to relate the Q's to T, and you have T1 divided by T1 minus T2. And this turns out to be 1 plus the efficiency of, so the figure of merit of refrigerator. Okay, so now I will give you this figure. You have something very similar, but there's a small subtlety here. You have to add 1 to here. Okay, so this is your eta for heat pump. So 1 is here, and you get a diverging ratio, diverging eta, when the ratio between T2 and T1 is 1. So when these two are the same, this should up. Okay, so this is really for heat pump. Okay, this is actually a very good thing if you think about this. This is very efficient for heating. You can very good for heating the building. Why do I say that? The reason is this: you usually, at least for Hong Kong, what we really want is an indoor temperature, which is not too different from the outdoor temperature, right? Our temperature difference is never that great. And actually, this applies to many cases. Let's say if you want your room temperature, this is now your room. So if you want your room temperature to be 300 Kelvin, which is comfortable, and your outdoor temperature is of the order of freezing point, but let's say to illustrate this, I calculated this for 280. And that's again another thing you should really appreciate this. I do not really need Q1, Q2 because they are related. Okay, so what do I get? My eta plugging in this number is 15. You can try yourself. So you have 300, and then this is 300 minus 280. So you have 15. Okay, so this is kind of good. This is nice. Even if you have a temperature a little bit lower, you still get. Okay. Okay, what is this concept? What is this figure of merit telling you? So let's be a little bit more concrete. So this is an example. Now, this is defined as Q1 divided by W, right? So if I want to get 10 kilowatt of heating, so this is I divide by the unit time. So you have to, this is really heat given in joule. So if I divide by the unit time, I will get the power. So if I want a heating power of 10 kilowatts, you can calculate how much you have to pay. So this will give you a number of 6.67 kilowatts. Okay, I have a heater in my office. There's about 2 kilowatts. So 3 times I run 3 heaters, I will be able to generate 10 kilowatts. Right, so I run 3 heaters of 2 kilowatts. I will be able to get 10 kilowatt. I pay less. I pay 6.7 kilowatt to get 10 kilowatt. That's because my heat pump is helping me to steal some heat from the environment. Okay, so this is actually quite nice. You pay less to get the same. But for my heater here, I put 2 kilowatt to get 2 kilowatt. And what is the catch? If this is so good, why do we not see this more often? The reason is very simple. You have to buy this heat pump, and the price you pay might take you a long time to offset the electricity bill advantage, electricity bill saving you gain by this 3.3 kilowatt. Okay, so that is the reason. Okay, and the other thing, when we discuss heat pump, we should also mention the other fact. So now look at this diagram. When T2 and T1 are very different, let's say if you try to build a heat pump, and really, I make a mistake. Okay, yeah, let's see. So I think you are right. Okay, then it's even better. I think it's this. I think you're right. Okay. Then you should laugh even more, right? So you pay even less. Okay, so okay, I'm sorry about this this calculation. Wait a minute. This is okay, but anyway, the message is this: you pay less to get a lot. Okay, but this kind of breakdown, you know, eventually it breaks down because you see, you will reach 1. I didn't draw this quite well. This is quite flat very quickly, right? So what is the meaning when this reaches 1? So when this reaches 1, it's kind of a silly idea to build a heat pump. Why you will say, that's why I don't like the word efficiency. Some people will say efficiency of 1 and treat it as 100%. But I like to use the word figure of merit because at this point, heat pump is not necessary. Why do you need a heat pump in this case? This heat pump, you might as well just plug it to an electrical heater and directly warm everything, right? Because when this happens, remember, this is my definition, right? And that is to say, my Q1 is almost the same as W. Okay, so all the work I put in will get transferred to Q1. So in this case, I don't need a very expensive structure. Imagine you buy something that looks like air conditioner, but it's called heat pump. You know, you have a lot of infrastructure to you need. You might have to drill a hole. You might have to do a lot of stuff, pay a lot of money just to get this. Right. So if you take a hair dryer and blow air into the room, you might as well get the heat this way. Okay, so heat pump becomes less. So the heat pump become almost redundant. I would say less efficient, less functional. If T2 is too low. Okay. Okay, I think that is all I want to say for this chapter. It's about heat engine. And let's take a break. And when you come back, we are going to talk about this big thing, Clausius theorem. This is the next chapter, but it's a good time to talk about this. This is very important, and it really leads to the notion of entropy. Okay, so let's take a break. We can come back at 1:35, and we are going to do this slowly and carefully. And still, we need to use engines. We are still going to draw some engines, and then we are still going to discuss the situation in relation to the statement, the formulation of the second laws based on those two impossible engines. Okay, but it will lead to a very cute result. And this is the Clausius theorem. Okay, so see you again at 1:35. Okay, welcome back. We are entering chapter 4, and this chapter is kind of heavy. We will hopefully reach the definition, the notion of entropy today. Okay, so the first one I want to talk about is Clausius theorem. So let me motivate you by considering the case we have been talking about. And here's the one. So I'm going to consider this heat engine H. Okay, and this heat engine will operating between the two reservoirs at T1 and T2. Okay, now I will switch to T rather than theta. Okay, the two reservoirs are at T1 and T2, and then I want T2 to be at the lower temperature. Okay, so T1 is the hotter reservoir. Okay, so Clausius theorem, Carnot's theorem told us the best we can write is this. Okay, and what can we now after today's lecture? After what we talked about in the first half of the lecture, we know we can then get something else, something different. Okay, so the efficiency is always related to Qs. Okay. And where is the inequality? How do you deal with this inequality? So you need to write a little bit different. Now you see this is the key. For the Carnot, we know how to write the efficiency. Okay, so to be very careful, I'm going to label this as ref. So this ref is to remind you that Carnot engine is strictly reversible. Okay, so I can have something like this. And for a reversible engine, we know this is related to the temperature ratio. Right? This is how we we came up with the definition of the thermodynamic temperature. And it can be shown that this is equivalent to the Kelvin scale. So I'm going to, from now on, just take this as the Kelvin scale. Okay, so here, remember this inequality is here. So what I can then write is 1 minus Q2. One more line is better. It's less than or equal to 1 minus T2 divided by T1. And this leads to Q2 divided by Q1 is greater than T2 divided by T1. Okay. Now remember what is Q2 and Q1? Q2 and Q1 are the heat flows for this hypothetical engine H, which we don't know much about. The only thing we know is this engine is operating between the same reservoirs. Okay, now this is what we have seen before. And to really proceed, I need to begin to worry about the sign convention. So we have been a little bit loose about this, but this is a very conventional way to do this part. So as I say, this really means the absolute value. Okay, so it better be, otherwise you have a trouble here. All right, this is always positive. But now I need to be very careful with the sign convention. So from now, I will take extra care of the sign convention in order to logically follow to Clausius theorem convention. What is our sign convention? So if the heat enter the system or the engine, this is a positive. Then we use positive Q. Okay. Now, so in this case, heat always I'm talking about a normal engine. So my heat is entering the system from the high temperature side. So now this is, I need a different symbol. So this is a high temperature. And we know the higher temperature reservoir is labeled by 1. So in this case, we do not change the sign of Q1. Okay, so again, I don't want to keep labeling the absolute value. And similarly, I can say the heat leaving the engine will eventually flow to the lower reservoir, so lower temperature reservoir. So QL in this case has to be minus Q2, right? We call the lower reservoir T2. Okay, and now this should be better. Okay, you plug this back in, you have so in this case you plug it back here, you get minus QL T2 is the same as QH T1. Okay, so I move everything to the right. So I will have QL divided by T2 plus QH divided by T1 is less than 0, less than or equal to 0. Okay, and this can be written in a very compact way. What we can then say is this: we only have two reservoirs. We only have two places to exchange heat. The engine only exchange heat with two reservoirs. You can think of it this way, right? Our engine is really this engine is really exchanging heat. This engine is exchanging heat with two reservoirs. Okay, so this is the usual engine. Let me draw it. This is 2 is lower. Okay, so this is T1, T2. Okay, so I can write it like this. I can write it as a sum of heat exchange, taking into account of the proper sign convention, and I exchange heat at temperature T, and this has to be less than or equal to 0. Okay, and then I can label something like this is the first reservoir, or this is the ith reservoir. Okay, and most importantly, look, for this engine we have been studying so far, there are only two reservoirs. So once I include all this, I actually go back to the same state, right? So this is if you think in terms of the indicator diagram, after I do all this, I actually go back to the same state. And therefore, I can also write it like this. I can write it as a cycle. So for one cycle, I will exchange heat with all the reservoir, and I must have this result. Okay, so now the questions a very natural question to ask at this point is this. Can I have a general cyclic process? So if I have a general cyclic process, that's to say, I can exchange heat with more than one reservoir. I can have many reservoirs. My engine is exchanging heat with all reservoir. What happens in this case? Okay, and the preview is this. If you have something like this, for the general case, you still have this. So it's a cyclic. Once you go back to, you finish the whole cycle, you count, you do the accounting as you go, you will still have this result. That is for a general case, a general process, cyclic process with a general engine. So this engine H, again, I do not say too much about that. So now this engine is operating with such that this is exchanging heat with many reservoirs, even if the number of reservoirs is large. Okay, so this is this is the starting point. Eventually, I want a closed form that allows me to get the closest inequality. Okay, let's begin to do this. So this is a little bit, you need to be very careful. There are some very important argument here. Okay, I'm going to consider the situation like this. I'm going to consider a cyclic process. Let's suppose this is my engine. Suppose this is my engine. This is some kind of process, right? So I can imagine, for example, exchanging heat with this segment of my cycle, and at this segment of the cycle, I am exchanging heat d bar q with a reservoir at T I. Okay, so let me draw it for you. This is a very schematic way of drawing things. This is like my machine, my engine, this engine exchange heat d bar Q1 with reservoir kept at temperature Ti. Okay, so in this case, and of course I need to draw the work done. So I can extract some work, which I will call delta W. Okay, so for the heat engine we are familiar with, we will have I equals 1 and 2. Okay, so I now try to make it more abstract in the hope that I will get something more powerful than just a simple heat engine I discussed here. Okay, so now this is more general. I condensed that diagram I drew to this diagram. Okay, so then let's write a few things about this engine. We need a lot of space. Actually, I should have drawn it a little bit lower. Anyway, let me start. Okay, so I'm going to use this d bar Q to denote the infinitesimal amount of heat entering a particular part of the cycle. Okay, so this is if this is positive, it will be enters, and this sign convention will be taken care of. If you have heat leaving, you have a minus sign, and you can convince yourself that in the end, once we finish this, you'll be able to get this result. You'll be able to get this result. Okay, so this I will be something is an index for me to do summation. So I will finish this and enter the particular part of the cycle. Okay, so sign convention is important here. So if this is negative, it means heat flows away. Okay, now at this point, the important point is this. I write this. I say now this is general. Okay, I didn't say the same I can automatically be flipped. Okay, so for example, if I choose I equals 10, I did not say d bar Q subscript 10 can take a negative value. What does it mean? It means I did not demand the process to be reversible. Remember, reversibility means I flip the direction of the arrow. And what does it mean? When you are really careful about the sign convention, this also means you flip the sign, right? So I do not, so here, careful, you need to, so warning. The segment can be okay. We don't know. We simply don't know. I didn't say it has to be. Okay, so if you go around, so suppose you have all this I, but after you do enough I, you go back to the same point. This is the meaning of cyclic process. And because you go back to the same point, the internal energy cannot change. Okay, the internal energy after one cycle cannot change. From the first law, we know in that case, we have this relationship. Okay, now this I will be a cycle. We can keep adding this and then count. But then you have to worry about the internal energy. But if this is a cycle, then from the first law, du is 0. Sorry, let me say this again. Now, from the first law, This has to be true because du is 0. Why du is 0? Because u is a function of state. Okay, so this result is the first law. This is the first law. This equation here. Let me draw it a little bit. This is because of the first law. Okay, now this is what I set it up. This is how I set it up. But I want to do something more. Okay, now what I will do is this. I'm going to do something interesting. I want to do some accounting. I want to count this heat. So I need a way for me to keep track of this, how much d bar q I put in. So what I will do is this. I'm going to connect this to a Carnot cycle because I know Carnot cycle very well. I know how to keep track of everything because in this case, heat flow is just a ratio between the temperatures of the reservoir. Temperatures of the reservoirs. So I can set up something like this. I can use many Carnot cycles. So this is actually C sub I. So for the ith Carnot cycle, I'm going to use it to connect. I'm going to use it to look at the heat transfer between a fixed reservoir and the ith reservoir. Okay, so this is the setup. And in this case, I will get some work done, dwi. Okay, do you get this point? When I go to a different segment, let's say I go to segment number 5, I'm going to change my index I to 5, but I'm always going to operate my Carnot cycle between T sub 5 and T fixed. So this T fixed really takes the meaning of the T fixed. Suppose I have a huge reservoir, which I know how to use it as the high temperature reservoir of all these Carnot engines. Okay, and nobody can stop me from doing this. Okay, so I just did this, and this is the setup I'm going to analyze. Okay, so I can connect a Carnot engine. Okay, so for this Carnot engine, for Carnot engine C, C sub I, this is the Carnot engine. Sorry, this Carnot engine C sub I. So this one is Carnot. What do I have? As I say, I know this engine very well because I know how to take the ratio between the heat, right? So the ratio of the heat flow, right? This Q high divided by Q low is T fixed divided by T low. Okay, so I'm going to put this in the mathematics form. Okay, I don't want to introduce another symbol, but what is this? This split into these two. So I'm going to just write d bar Q I plus dwi. Okay, d bar qi dwi. Basically, this is this one. Okay, this divided by T fixed is the same as d bar qi divided by Ti. Okay, so this is a heat flowing into the Carnot. This is the heat flow out from the Carnot. Okay, so I can, in this case, I can write this. This is the physics and this is the mathematics. So the mathematics, we just rearrange it. I think you have to trust me on this. D bar Qi. Okay, so from here I rearrange, I get this. Now I think you have to trust me on this, but as Andy shown, sometimes it's better to check again. So let me see. I think This is correct. Is it correct, Andy? I think it's correct. You can verify. Okay, so now, this is not too difficult to remember. Okay, so I'm going to continue from here. Okay, this is the same trick we used before. We are going to look at the composite engine now. So the composite engine will give me, now what is the composite engine? So I will have the Carnot, all these Carnot engines, plus this engine at the bottom. Okay, so if you look at the composite engine, this one. So for the composite engine, the total work done, and this is the total work done per cycle. Now when you go, this is why do we use per cycle? Because I will write it first. So this is from the bottom you get delta W. Why? Because this is written here. Once you go through the cycle, you get this result. Okay, so the total work done per cycle from the lower part will be delta W. Okay, from the lower part will be delta W. And from the top, you have to go around and sum, right? Because now you have I going from 1 to maybe 2000 until you hit the same state. Okay, so you have to sum over the same cycle. You have to sum over all the i's. That will give you the cycle. Okay, so this is the same as you have to sum over this d bar I, d bar wi, and cycle. Okay, I'm trying to explain this slowly. Okay, now if you look at the composite engine, right? How do you draw the composite engine? The composite engine will look like this: T fix. You take in some heat, and all the i's become internal, so we don't really care anymore, right? So the net output is this total work done, delta W plus sum over the cycle D, right? So if you go up a little bit, now you look at only the composite engine. What do you have? You have the reservoir at fixed temperature, and all this becomes internal. And what you have is delta W plus sum over D bar W, which is this picture here. So far, so good? Okay, here is the key of the argument. If you draw this picture, if you draw it with this arrow down, this arrow out, this is not allowed. Why? Because this violet, this is one of the impossible engine. This is a not C. Right? Sorry, this is a not K, because you take all the heat from one single reservoir. Right? T fixed. This is one single reservoir, and then get a net work done. So this is not allowed. This is this picture. If you draw it like this, is actually not K. Okay, so what do you do? What do you have to demand? So for this to be useful and not violating the second law, you have no choice but to demand to flip the arrow. Okay, so you'll be fine if this is negative. Okay, if you draw it this way, If this is positive and arrow is this way, this is not allowed. This violates the second law. So to save the situation, you have to demand this to be negative. So if you draw it this way, and this gives you negative quantity, so effectively this is work going in rather than work being extracted from the system. Okay, and that's all I need. This is the end of the physical argument, and then you just look at this. You have delta W. You can express it as the sum of d bar q, and you have sum of d bar wi, and d bar wi is this thing. So you have another sum of d bar q. Okay, so I'm going to do it. This is important. So sum over the cycle, and this is the first part of the argument we did earlier for the lower part. And then this one will be a sum over the cycle. You have this t fixed divided by ti minus 1 d bar qi. And this, we already say, has to be less than or equal to 0. Okay, so this one, this is this part here. And this is this. Okay, and you get very nice stuff because you have sum over the cycle for d bar qi, and here you have sum over the cycle for d bar qi with a minus sign. So you have some cancellation between this and this term, this term here. Okay, so you have sum, in the end you have sum over cycle t fixed divided by ti and d bar qi. This has to be less than or equal to 0. Okay, you already can sense where we are going. Now this t fixed is fixed, so you can take it out, and it doesn't affect the inequality sign. Okay, and this t fixed is positive, is fixed and positive. You can take it out and Q it, and you get the your desired result. So what you have is this. Okay, t fixed is out. You have d bar qi, and this is written like this. Okay, so usually we like a more compact symbol. If you sum over all these infinitesimal d bar qi, and we might as well use the symbol we like, and that is integration over a closed loop of d bar q divided by t, and that has to be less than or equal to 0. Okay, so this is the important inequality. This is called Clausius inequality, and it's discovered by analyzing engines. Okay, and how do you understand this? The way to understand this is actually here. Now this is more transparent actually. When you talk about d bar qi, this is a heat exchange with a particular reservoir, and this reservoir is kept at T sub I. So this is the temperature of that particular reservoir. You label with the index I. Okay, so this is really the meaning. The meaning is just one line above, but usually we like to write it like this. Okay, this is okay. Now this is cool, right? I didn't say much about this d bar q or d bar qi. Now, from now, I will say a little bit more about that. Okay, this is a statement. This is a statement you must be able to handle because I already warned you. So if the entire system is reversible, okay. Now, if you have one particular segment, let's say one of the eyes is not reversible, then you can only stay here. Okay, you get this result. This is an inequality. As long as you satisfy this inequality, you does not violate the second law. Okay, so now why is the sign convention important? Because you really want to you are comparing this quantity with zero, so the sign convention is important here. Okay, so if the system is reversible everywhere, then for OI, I can set d bar qi to minus d bar qi. Okay, so this is important. It has to be for all, otherwise this argument will break down. Okay, in that case, you flip the inequality. So in addition to this, you need to satisfy another one. So you, in this case, we additionally have d bar q, right? If you flip all this d bar q, you flip the sign of inequality, right? That's coming here, right? Give it a minus sign, and you get this result. So this is an additional result. Let me say this again. I know maybe it's boring for some of you. Let me say this again. This is additional, which means you have to satisfy this one and this one. So the net result is if this entire cycle is reversible, you have d bar q over t is precisely 0. Okay, so to emphasize this is important. I'm going to add this for you. Okay, so if the process is reversible, you have this plus this, and that gives you this. At this point, it would be really nice if you maybe some of you look at this and begin to feel, wow, this is amazing. I have seen something big here. In that case, congratulations. So indeed, there's something big here. Okay, what is that big thing? The big thing is this. By analyzing reversible process, we have this result. Okay, and that result basically tells you if I integrate this quantity around a closed path, the integral is 0. Okay, and you can only do this, you can only achieve this if this integrand is the differential of a function of state. Okay, that is to say this whole thing is consistent with the definition of an exact differential. Okay, so here we are going to define ds to be d bar q ref divided by t. Okay, and this S is entropy. Okay, so another way to say that is through this analysis, we've found the integrating factor for the heat flow. And that integrating factor is 1 over T. And that leads us to the notion of entropy. Okay, now this is really cool actually. And we can say more about this. So here, I think this is a good point to stop. Okay, so next lecture, we are going to learn more about this entropy, and we are going to get some result, some important result, and then we are going to analyze a few situations, a few very standard classic situation to say something about whether a given process is reversible or not. Okay, so these are really very important materials of thermodynamics. They are standard and they are very important. Okay. Okay, thank you very much.